All right, let's talk about the homework. Pretty much this homework is plug and crank or derive, but get you started on how I define the variables in number one. I decided to call the velocity for G, Vg, and the velocity for F, F dot, and then from then it's just like we did in class. You plug in where you have G double dot, you're going to turn that into V sub G dot. And where you have G dot, the second derivative, you're going to call that Vg. And then you shove all the dots on the left and all the non-dots on the right, and you put it into a matrix. The order that I did for the vector was like that. And if you do that order, this is the matrix you should get. And then you find the eigenvalues of that. Of course, this is going to be multiplied by this is x dot, this is x. And you'll have a vector here with the forcing function there. So obviously there's the answer, so make sure you show the steps of the substitution and then rearranging the equation before you put it into that form. Does that make sense? Yeah. Yeah, actually you could subdivide it, but I want it to be the 4x4, the full thing. Yeah, because of the way that it's block diagonalized, it's actually, they're independent in effect, yeah. And again, I didn't want to make it too complicated, just this is just you going through the process of doing this. And then part two is you're just calculating the vector algebra. So you should get the answers that are in the book, the equations that it says derive. And really what you're doing is you're taking the products. We have this I matrix, and you multiply it by P dot, Q dot, and R dot, the vector. So you're just taking the vector matrix product to get the first couple of columns in the equations. And then the hard part is doing this cross product. So you're taking omega b cross hb, but hb is I omega, right? Right, so you end up with a matrix or here, or a vector here that then you have to cross product. So you just have to work through the algebra here. So this takes a bit of time, but just go through the steps of taking that product, and that's it. And what this is leading to, this, you're just doing vector algebra, but this is leading to the equations of motion that we're going to talk about today. So this is, you're doing some of the work that we're going to be talking about today for this. Is everybody good on this? Again, it just took me a page of algebra, but just crunch through that. So this is HB dot. And then this is omega cross HB that you're doing here. And you just add those two terms together and you get the equations that were shown. Okay. Any questions on the homework? Anything good? Yep. Okay. All right, so we're going to talk about the aircraft. Equations of motion. And these are based on Newton's laws. And these can be done in an Earth-fixed axis, which is an inertial frame. Or in the body-fixed axis that's attached to the airplane. And so the differences here are say that's attached to the Earth. Z is pointing toward the center of the Earth. X is pointing north and Y is pointing east. Did I get that right? That's Y needs to be this way, so that X cross Y is Z. Yeah, so X is pointing north usually, Y is pointing east, and Z is pointing down. So that's, we're considering an inertial frame. It's non-accelerating, non-rotating. Although the Earth rotates, we're going to say that rotation is small. And then up here we have an airplane with its own X, Y, Z body fixed axis, and that can rotate and move with the airplane. So this is non-inertial. This thing is inertial. And so in the Earth-fixed axis system, and Newton's law looks real familiar. It's that the sum of the forces is equal to the mass times the acceleration, and this is for a constant mass. If the mass is not constant, you have d, the derivative of the momentum, m times v, right? But we're going to assume the mass of the airplane does not change with time. If you're expressing these vectors fe and ve in the body fixed axis system, what that means is that the i's and the j's and the k's change with time. So not only do you have derivatives this is the body fix. Not only do you have derivatives of u, v, and w, but you also have derivatives of I, j, and k. And you should have done this in dynamics and in spacecraft dynamics. It showed that in the rotating axis system, you get this extra term that's omega cross VB when you're in the rotating axis system. So omega, this is the angular velocity of that thing rotating. And really, this is the derivative of u, v, and w. And then this is the derivative of I, j, and k that are moving. Because you've got VB as u, I guess it'd be better to write this like this. ui plus vj plus wk. And so you get two terms. You get the derivative of u, v, and w, and then you get the derivative of I, j, and k, and you can write those derivatives in terms of omega cross v. You can show that. And should have done that in dynamics. So we typically work in this equation because we know the lift, drag, and pitching moment are all of the forces in the body fixed axis system, right? Lift is upward relative to the wind. It has nothing to do with the earth. Drag is backward, body fixed, and thrust is forward. So most of the time we deal with these equations in terms of the body fixed axis system because it's easier. And it's like you're the pilot on the airplane and you're in that axis system, so you see the velocities and the angular velocities of the airplane for that. And then Newton's force laws, we also have the moment laws. The sum of the moments is equal to angular accelerations times I, and that's what this thing is working on that you're doing the vector algebra for. So the angular momentum in the earth fixed the total moment applied is equal to the derivative of the angular momentum vector h. And in the body fixed, we have the same thing. Because this thing is rotating, the axis system is rotating, we get an HB dot, and then we get an omega cross HB. And the other reason we do things in the body fixed axis system is you can write HB in terms of I, this moment of inertia matrix, and those are constant with time if your axis is attached to the body, because the body is rigid and it stays in the same position relative to x, y, z. And to define everything that goes in here, omega, of course, is P plus Q plus R in the I, J, and K, or sometimes we'll write that as a column vector, P, Q, and R. Sorry, I'm using lowercase here. Like that. So all of this is just dynamics. There's the omega vector. This is the sum of the moments is the I times omega, the derivative of that. And then I in the body fixed are these mass moment of inertia terms. Like that. And if you notice in the homework problem that you're doing, we simplify this because airplanes are symmetrical. And so any of the cross products that involve y, we knock out for a symmetrical airplane. And it's symmetrical about the x, z plane, and xz is the vertical plane, right? Look at the figure here, xz is this plane here. And so what we say is if we have a left wing, we have a right wing that's identical. If the fuselage is curved on the left, it's curved in the same way on the right. And so those ixy's and izy's are 0. Because those are those integrals that you've defined in dynamics. And the reason that for the symmetrical airplane, this one and this one is 0 is because you got y in this integral, and so you have an equal mass on the left side and on the right side, so you have a plus and a minus and they cancel out. Yeah. Oh, did I not do that? Right, sorry. So this is what I wrote. Sorry about that, guys on Zoom. This is what I just wrote, the definitions. And these are the ones that are 0 for the symmetrical aircraft. Because it's there's a symmetry in y, plus and minus y here. So what I'm going to do next is take this equation and we're going to plug in omega in terms of P, Q, and R, just so that we can we're going to express it in terms of 3 equations rather than a big vector equation. And then we're going to plug in VB as UI plus VJ plus WK. And so we're going to get dynamic equations for U dot, V dot, and W dot. Those are the accelerations, the linear accelerations. And then the forces we express in general, and then we'll fill in those later. What do I call those? FX. Yeah. So we say here's the force in the X direction. Here's the force in the Y direction. Here's the force in the Z direction. And then we'll have to fill in what those are, because we'll have to fill in, well, which way does gravity act? So we'll have to have the gravity vector in terms of X, Y, and Z. We'll have to have the lift in terms of X, Y, and Z, the drag in terms of X, Y, and Z. So we'll fill those in a bit. But I want to do this vector algebra, and then what you're doing is the same thing in homework, is the vector algebra for the momentum equation. So let's do the hard one first. We're going to do mass times omega cross VB. Fx, well, we've already done Fx, or FB, that's easy. And then VB dot is going to be easy, it's just the derivative, right? So what's your favorite way to do a cross product? Do you brute force it? And what we got is PQ that crossed with that, right? So we could do I cross I is 0, I cross J is positive K, I cross K is negative J, right? So on. Is there another way you guys typically do cross products? You guys remember? How would you do it? You do what? The determinant. So you would write one way that I didn't learn, but I learned actually in this class from you guys who learned how to do this, is you write IJK here, right? Then the first of the cross products here. Is that what you're talking about? Yeah, and that's an easy way to do it. So then you get I, so expanding about this, times QW minus V. Oh, I need to be careful, make my R's look like R's, right? This is a V. Then you get a minus J because it's the middle one, times PW minus UR, and then expand about the K. PV minus UQ. And so that's what goes into that term. And then VB dot is just U dot I plus V dot J plus W dot K. And we just differentiate U, V, and W. Why? Because I, J, and K, we've already taken care of the derivatives of those things because they're moving in the omega cross thing. So that gives us the force equations. We'll write these as column vectors now. So the I equation, so we're going to grab the I stuff, and that goes into the first equation. We'll grab the J stuff, and that goes into the second equation, and the K stuff, and that goes into the third equation. We're going to write these as column vectors instead of IJs and Ks, and then the left-hand side is just the forces Fx, Fy, and Fz are equal to M times the VB dot so here's the I stuff, here's this K stuff, and so these are what are called the force equations. And so you might be saying, well, we really haven't done anything, and you're absolutely right. We've just done Newton's laws in a body fixed axis system, and then we plugged in our terms for the velocities and the angular velocities. So we still need there's still some work here to put in the lift and the drag and gravity vector, etc. here. But it makes sense, right? It's Newton's laws. Here's the sum of the forces in the x direction. Here's the acceleration. This is the acceleration due to the fact that we're in the body fixed axis, rotating axis. Same thing for v dot and w dot. And then what's left to do is what you're doing in homework problem number 1, is the matrix and vector algebra to fill in the moment equation. So you're doing the hard work in the homework, and I'm going to write down the answer. So this is what you're doing. And so you're carrying out these products. This is the rolling moment, pitching moment, yawing moment. We've been doing that all along. You're calculating this product here. And then the product, this cross product here. And you get the equations that are in the book, and these are the equations that essentially say the sum of the moments is equal to the angular acceleration, P, Q, and R. And then this is the extra stuff due to the fact that we're in a body fixed axis system that's rotating. And again, this has nothing to do with airplanes. This is just a rigid body that's rotating. That's all it is. And we fill in the aerodynamics here, and then it becomes an airplane. And so when you're done with the symmetry here, you should get these equations. And notice this is from the book. I tend to write IXX, and he shortens it to just IX in the book. So if you see IX, he's really saying IXX. So these are the equations of motion. This is just essentially preliminary work getting set up, because the